Hi class, we are on chapter 7.4. We are going to be looking at quantifying heat and work. So heat is the exchange of thermal energy between a system and its surroundings. We've already been covering heat, so hopefully you're getting more comfortable with understanding with the system and surroundings. Heat exchange occurs when the system and surroundings have a difference in temperature. Temperature is the measure of thermal energy within the sample matter. So basically what this is give an example of a coffee cup with hot cocoa in it, and you're sitting in a cold room. There is a difference in temperature between the cocoa and the surroundings, and the heat will always leave from its source to the colder region. So you are losing the heat into the surroundings. There is a temperature difference there. The thermometer, or temperature, is a measure of the thermal energy. So this is how we are able to determine temperature differences from final and initial. Eventually, what will happen, based on this last sentence, heat flows from matter with high temperature to matter with low temperature until both objects reach the same temperature. That basically means that your cocoa is going to eventually lose heat, the surroundings are going to gain heat, and there is going to be a temperature that both are met at, and that's going to be thermal equilibrium. Okay, so let's go on to quantity of heat, energy absorbed, heat capacity. So when a system absorbs heat, its temperature increases. The increase in temperature is directly proportional to the amount of heat. Basically what that means is that if one goes up, the other one also has to directly go up. If one goes down, the other one has to directly go down. So if there's an increase in temperature, that means there's an increase in amount of heat absorbed. If there's an increase in amount of heat absorbed, there is an increase in temperature. They are directly proportional. The proportionality constant is called the heat capacity. It's a C. Now, as we start getting more and more into this, you should become fairly familiar with, learn what units go with what. That will help you solve problems. Even if you don't know what the problem is, if you know what specific heat capacity, what units go with that. Heat capacity, Q. If you know what units go with this stuff, then it will help you solve a problem, because you can break it down even only partly by using the units. So this is heat capacity. It has two units. It's either joules over Celsius or joules over Kelvin. Why does it look that way? Because remember, joules is Q and temperature is T. So they have this rearranged a different way. But if you solve for C, then this will look matching these units. The larger the heat capacity of the object being studied, the smaller the temperature rise for a given amount of heat. What this means is that if you have a very large value of heat capacity, it's going to take a lot of energy before that temperature rises even a little bit. It has the capacity to hold a lot of energy. So factors affecting heat capacity. The heat capacity of an object depends on the amount of matter, its mass, how much mass. That will affect how much energy it's going to take to rise the temperature of that object. 200 grams of water requires twice as much heat to raise the temperature by 1 degree Celsius as much as 100 grams of water. So you definitely need to know what the mass is. The heat capacity of an object depends on the material, because certain materials have different values of specific heat capacities. And if it's a low value, they do not retain heat very well. But if it's a high value, such as something like water, you're going to need more and more heat before you're even going to raise that temperature. So 1,000 joules of heat energy will raise the temperature of 100 grams of sand by 12 degrees Celsius, but only raise the temperature of 100 grams of water by 2.4. This is a perfect example of when you go to the beach. You go to the beach and you're barefoot, your feet are burning on the sand, because sand has a very low specific heat capacity, doesn't retain heat very well. But water does. So when you get to the water, it's really cold, you want to jump in, and then you run out screaming because it's really cold. So specific heat capacity is a measure of the substance's intrinsic ability to absorb heat. Intrinsic property is inherent to the sample. This means it's something that is unique to a particular substance and different from another substance. So it's kind of like a fingerprint. It can be used to help identify a substance by process of elimination. What's the density of it? Does it conduct electricity? What's it reactive? And it does not change with the amount of material being measured. So this is something that's within. So the specific heat capacity is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now, specific heat capacity has 3 units. It is either joules per over grams Celsius or calories over grams Celsius. There are 3 units to it. This is never negative because this is describing a heat value for substances. And what it is that the higher the value of a substance, a specific heat value substance, that means it takes more and more energy to raise it even 1 degree Celsius. So if you take a look here, you see metals have very low specific heat capacities. That's why we use them to cook food. But yet water is very large, so it takes a lot of energy to raise a temperature. That's why there's a concern about the ocean temperature rising, because if you understand how much energy it takes to rise the temperature of the ocean and how vast it is, it's really disturbing. Okay, so quantifying heat energy. The heat capacity of an object is proportional to its mass and the specific heat material. So again, there's that example of, if we go back, 200 grams of water will have a different value over 100 grams of water. So having the mass is very important. You also need the specific heat material, which is this list here. We can calculate the quantity of heat absorbed by an object. So quantity of heat, that's Q. That's a fancy word for Q. What is Q? Q is either joules or it's cals. So you definitely need to know. This is where you get a piece of paper and you write down each of these and what the units that go with it, and that will also help you get an answer right, because quantity of heat has 1 unit. It's either calories or it's joules. By an object, we know the mass, the specific heat, and the temperature change. So if we look here, there's that quantity of heat. It's either in joules or cals. That's 1 unit. This overall here is, if we change this and solve for C, it is specific heat capacity, which is joules over grams per Celsius. Mass is grams. This is the difference on initial temperature, final temperature minus initial temperature. So again, this is just an example of what I talked about, sand and water. Water absorbs a lot of heat energy without a big increase in temperature. So temperature difference in summer between Sacramento and San Francisco, one is inland, one is a coastal, could be as much as 30 degrees in Fahrenheit, 18 degrees Celsius. It is because the sun's beaming down in the same general area, but water stays cold because the specific heat value very large. Everything else tends to be a lot lower. It does not retain the heat. The other aspect of this, that's why the ocean communities are so cool, and they're also not as cold at night, because all that energy that the ocean took in the daytime, it cools off very slowly, so it relieves the heat, and that actually makes these coastal communities, even though we might think they're cold, they're actually a lot warmer than they would be if you keep going inland in the same area. Just go parallel inland and you will see that those areas are colder and colder and colder because they don't have that buffer of water to protect and release heat into the environment at night. So you are cold weather camping and decide to heat some objects to bring into your sleeping bag for added warmth. You place a large water jug and a rock of equal mass near the fire. Over time, both the rock and the water jug warm to about 38 degrees Celsius, 100 degrees Fahrenheit. If you can bring only one into your sleeping bag, which one would it be and why? So I'm just going to jump to the answer and let's break it down. Water. The rock is going to probably be made of metals. Metals do not retain heat very well. So it might get really, really hot at first, and then it's going to cool down very, very fast. So you're going to lose that warmth. Water, on the other hand, will retain it longer, and it will release heat slowly as it cools. So if you want to have something, water is going to be what you want. So it would be A. It's not going to be D, because D is saying that it's going to absorb heat as it cools. It can't do both. That's not going to be possible. Okay, so thermal energy transfer. When two objects at different temperatures are placed in contact, heat flows from one material at a higher temperature to a material at a lower temperature. This is the amount of heat energy lost by the hot material equals the amount of heat gained by the cold. Remember, energy is not created nor destroyed. So if it's lost from one, it has to be gained from the other, and the negative sign and the positive sign will tell you where it went. So a block of metal at 55 degrees Celsius is submerged in water at 25 degrees Celsius. So you kind of see this picture here. And the metal is hotter than the water. So thermal energy transfers heat from the metal to the water. And if we take the temperature, we know what the initial temperature of the water is. We know the initial excuse me, the final, I messed this up. This should be the final temperature of, no, it's initial, sorry, initial temperature of the metal. Then eventually what will happen, because they come in contact to each other, there will be a thermal equilibrium. They will eventually be the same temperature. One will give off the heat, the other will gain that heat, and it will raise the temperature of one, and the other one will lower the temperature until they basically meet in the middle, and that is called thermal equilibrium. So this is just a fancy ways, if you set them all up, you can solve for the variable that's not here, and that would be the final temperature of the metal and the water. Okay, so pressure volume work. Pressure volume work is done when there is an external volume change as measured against a pressure. So basically what this means is work associated with an observed volume change. So defined as a force acting through a distance. So remember, pushing a box over a distance. We're doing a force on that box, and that box is moving a certain amount of a distance. So PV work occurs when a force caused by a change in volume acts through a distance against an external pressure. What that means is, if we push this box, there's atmospheric pressure. That pressure is also pushing against the box, away against us. So we've got to push against that to clear that pressure to move that box. Okay, so pressure volume work is caused by a volume change against an external pressure. I think it's easier if I explain it this way. There's atmospheric pressure surrounding. So there's pressure, we don't feel it, but we have a pressure that's beating down on us all the time. We're used to it, and we only are aware of it when our ears pop. So that's the only time we're pretty much aware that there's an external pressure. So there's constantly a pressure beating down of air molecules. That's the external pressure. So if we use a force to push this up, it will travel a distance, and it'll change in volume, and it's being worked against the external pressure that's holding that piston in place. So now we're going to look at work of a gas. It's the external pressure, which is beating down by the change of volume. So you see there'd be a change of volume. This is the change in volume. This is change in volume is equal to the area, which is this whole area, times the height of it, of that change, or where it started at, and where it ended up. And then this is the fancy equation, W equals negative P delta V. The negative is there. Don't overthink it. That's just part of the equation. That helps if it needs to be positive. It helps if it needs to be negative. And without that there, we would get the opposite of what we want. To convert the units to joules, oh, I cut it off here. That's a J. Just know that's a J. See, there's the J. The picture's overriding it. Use 1.01.3 joules is equal to ATM times liter, or liters ATM is more like it. Either one, that makes it easy to write. So, because I think I have it here as liters ATM. Yes, I do. So, how does that come about? Because pressure is ATM, volume is liters. So there you go. That's where you get it. This is a conversion for it. So let's take a look at a problem. A chemical reaction is performed in a flask that is sealed with a piston. The initial volume of the system is 0.550 liters, and the final volume is 0.375 liters. The pressure remains constant at 1.00 atm. So I think I mentioned here, as long as the external pressure is kept constant, we can determine what the work is by the change of volume. So that's, the pressure is kept constant, but we know what the pressure is. We have an initial volume and we have a final volume. So now we have to figure out the change in volume, which we do. We have a final volume and initial problem, and we have a negative 0.175 liters. Okay, so the initial volume was actually larger than what the final volume was. Now we can plug in the pressure, and there's the negative. Don't forget the negative. Here's the negative. Then we calculate what the work is. The work that was done is 0.175 liters per ATM. Now, if we had to convert, if this problem was asking for joules, you do one more step with the conversion, and the conversion is here, and it would give you the answer in joules.